Alright, so in this video, what we're going to do is we're going to demonstrate how to show that something is a linear map. And to recall, what it means to be a linear map is two things. One, it's if I apply the transformation to the sum of vectors, that's the same thing as applying a sum to the transformation of the vectors. The other thing that it does is it takes the action of scaling a vector and then applying the transformation and allows you to apply the transformation, then scale the vector. In other words, recall a vector space. The vector space is fundamentally a place where you can add vectors and multiply by scalars. So what a linear map does is send them to a different vector space where the addition and the scaling hold just like you would expect, or hope at least. And so here's an example. I have a transformation from the space of polynomials to the space of polynomials. And what we do is we take a polynomial and we send it to 3 times itself minus 4 times its derivative evaluated at -5. Alright? I would briefly check, just mentally check that this will be a polynomial. Well, 3 times f of x. If f is a polynomial, if I triple all the coefficients, that's still a polynomial. The derivative function is also polynomial, and when I evaluate it at -5, that's a constant. I multiply by 4, that's a constant. A polynomial minus a constant is still a polynomial. So this is at least a valid map, and I want to show that it's a linear map, meaning I need to show these two properties. And so the first thing I'm going to start with is I'm going to start with showing the sum preservation. So I want to show that t of f of x plus g of x is equal to t of f of x plus t of g of x, right? This would preserve this feature here, right? And so to start with, I'm going to start with the left-hand side. So note, we'll start with the left-hand side, and when we start taking a transformation, we look at t's action on f plus g, and I should end up with 3 times f plus g, right? Minus 4 times the derivative of f plus g evaluated at -5. Alright? Now, one thing we should note is that multiplication is distributive. So, on the left-hand side, not on the left-hand side, but in this first term, I can go ahead and distribute that 3 through. In the second term here, what I first want to note is that derivation is also distributive in a sense, right? One of the first things we learn in an introductory calculus class is that the derivative of a sum is the sum of the derivatives. So what I'll end up with is f prime plus g prime evaluated at -5, right? But when I work that through, what I see is, that's f prime of -5 plus g prime at -5. And we'll note that my multiplication by 4 here should also be distributive. So what I should get is 3 f of x plus 3 g of x minus 4f prime at negative 5 minus 4g prime at negative 5. And I can group my f's and my g's together. And what we can see here is that, hey, when I group together my first collection, group of f's together, that is exactly the transformation of f of x, right? When we look up and see what f does, right? That's exactly what that is. And what this is then is exactly the transformation of g of x, right? So we've shown that this is that, so the sum preservation holds. Alright, the next thing we want to show is that scaling by constants is also holds as well. So in order to do that, what we want to show next is that if I take a transformation of some constant times f, that's the same thing as taking a constant of the transformation of f itself. And as before, what we're going to do is we're going to start with one side of this and reach the other through our manipulations. So when we take a transformation of c f of x, what we get is 3 times c f of x minus 4 times the derivative of cf evaluated at negative 5. Well, not much shocking happens in the first term. I'm just going to rearrange the c into 3. It doesn't really make a difference. Now what happens in the second term? Well, the first thing we want to recall is that, again, from an introductory calculus class, we know that the derivative of a constant times a function is the same thing as that constant times the derivative of a function. Like, the derivative of 2x is 2 times the derivative of x, right? And so this is all just, I can just go ahead and pull out my c, and what I'm left with is just f prime evaluated at negative 5 times 4, and then times my c, and then I should note that this whole thing is just c times 3 f of x minus 4 f prime of negative 5, right? But as before, once we reach this stage, we recognize that all we've done is written this as c times the transformation of f of x. So when I look at this, the transformation of a constant scalar times my vector is equal to that same constant times scaling my vector. We have achieved the preservation of scaling by constants. So we can say, thus, scaling by constants is preserved, and T is a linear map. All right, thank you.